right. Oops. Where's that? There we go. All right. So today we're going to be talking about something called balancing chemical equations or balancing reactions. It's a process by which scientists figure out exactly how many of each atom are in a chemical reaction. Yeah, Alexia, it looks like you're having some internet issues there. Leave her a comment really quick so she can see it when she logs back on. All right, there we go. So balancing chemical equations is what we're going to be going over today. And again, like I said, a lot of the homework questions I'm actually going to be going through with your guys' help here at the end of class today. Because the only way that you can really get good at this is by seeing and working on lots of examples. All right. So you may remember that on Tuesday, we were talking about chemical reactions, chemical changes. We talked about how we start off with our reactants on one side of our equation, and those get changed into the products on the other side of the equation. So we start off with our reactants. These are our like starting compounds or starting materials. And then our products are our ending materials, the stuff that we are making in the chemical reaction, the things that are produced at the end of the reaction. So this is kind of the very basic setup right here. You have some reactants on one side, they're gonna come and react together, and then you're gonna make some products at the end. So we talked a little bit more about different things that go on in chemical reactions the other day. We talked about how we can only rearrange the atoms that we have. So we looked at this photosynthesis equation, right? And I said on this side, we have carbons, we have oxygens, and we have hydrogens, C's, O's, and H's. And on this side, we have carbons, we have oxygens, and we have hydrogens, C's, O's, and H's. So we have the same types of atoms on either side. C's, O's, H's over here, C's, O's, and H's over here. We just, in order to create our products, we just rearrange them. We move around how the atoms are connected to each other. And that's what gives us our final products. So in this case, we have a whole bunch, so these numbers here represent how many of that particular molecule we have. So we have 6 carbon dioxides and 6 waters, and those are coming together to make 1 glucose and 6 O2 molecules. So we have our reactants that we're starting with, we have our products that we're ending with, and we are rearranging the atoms. We're reorganizing how they're attached to each other. So that's kind of the first 2 major things, right? Is that our reactants and products are different. So in order to be a chemical reaction, we have to make something that's new, that's different from what's over in our reactants. And number two, we can only rearrange the atoms. We can't create or destroy any atoms. We can't add in any extra types of atoms, like any nitrogens or any fluorines or anything over here. And we can't take away any of these atoms over here. If we have three different types of atoms on one side, we have to have those exact same three different types on the other side. No ifs, ands, or buts. But one other thing that scientists try to do when they're figuring out these chemical reactions is a lot of times, just like you saw with that photosynthesis reaction, they like to write out the reaction as this kind of chemical formula. So instead of writing out carbon dioxide plus water makes glucose plus oxygen, we like to know the exact atoms involved. So we use their chemical symbols, right? C for carbon, O for oxygen, and H for hydrogen. So we have CO2 plus H2O turns into C6H12O6 plus 6O2. So besides the actual chemical symbols that are in there, there are two different types of numbers that we can see. So besides these letters that represent the atoms, the chemical symbols, we also have those numbers. So the first number, the kind of the most important number that we're going to talk about today, if you forget everything else about the notes that we're doing today, remember coefficients. So coefficients are these big numbers here in front of the different atoms. And a coefficient just represents how many units of each substance that we have. So it's this big number that comes before or in front of the chemical symbol. So for example, we don't just have a CO2 molecule in this reaction, we have 6 CO2 molecules. We don't just have one water molecule in this reaction, we have 6 water molecules. We don't just have one O2 molecule that's produced in the reaction, we have 6 O2 molecules. The only thing that we do have one of is our glucose molecule right here. So if you don't see any coefficient, if there's no coefficient here at the front of our compound, that means that we just have the one. We don't have any extras. So 3 different coefficients in this photosynthesis reaction. We have a 6 in front of the CO2, a 6 in front of the H2O, and a 6 in front of the O2.
But how do you know how to separate the 6O2?
So that's actually what we're going to talk about a bit today, is how do you take like the base chemical reaction of CO2 plus H2O makes glucose and O2. How do you take that and figure out that this needs a 6 and this needs a 6 and this needs a 6? So that's actually exactly what we're going to be working on today, is how do you figure out exactly how many carbon dioxides, how many waters, how many O2s do you need in your equation? So the other number that you may have noticed are these little numbers down here at the bottom. These guys are called subscripts. These guys just tell you in this particular molecule, in this compound, how many of the different atoms are there. So these subscripts will always be the same. As you'll see in a little bit, these coefficients we can change around. We can make these numbers, these big numbers, larger or smaller, depending on how many that we need. But when you see these subscripts down here, I want you to think that they are like set in stone. We are not allowed to change them. We're not allowed to do anything with them. So in order to be a carbon dioxide molecule, you have to have 2 oxygens right here. And that's what this little subscript is telling us. In order to be a water molecule, you have to have 2 hydrogens in it. And that's what this little subscript down here is telling us. So these guys, you can consider, they're just part of the compound. They're just part of the molecule. They're not changing. They're going to stay the exact same all the time. It's only these big guys right here, these coefficients, that we can change and adjust if need be. So coefficients are these big numbers that tell us how many of a certain particle, certain molecule are in this overall reaction. And then the subscripts, little numbers down here, these just tell us about, in a thing of carbon dioxide, how many oxygens do we have? How many hydrogens do we have in this glucose molecule? It's just counting up the specific atoms in a certain molecule. Again, subscripts are permanent. Imagine they're on there in like Sharpie or permanent marker. You cannot change, you cannot do anything with these subscripts. You can only fiddle around with these coefficients, which is what we're going to be focusing on mostly today. All right, good question earlier from Mr. Rubin. Anybody else have any questions so far? Anything about the chemical equations or these coefficient numbers or subscript numbers that you're still a little lost on or a little confused about? All right, not yet, says Shannon. Good to know. Okay, so you want to figure out how many of each type of atom are in our chemical reaction. We know that we can't do it with these subscripts, and so we have to change around these coefficients. So when we do that, we're making something called a balanced chemical equation. So the goal of having a balanced chemical equation is that you have the exact same number of a type of atom on each side of the equation. So like for our photosynthesis equation up here, however many C's we have over on the reactant side, we should have that many over on the product side. However many O's we have in total on the reactant side, we should have that many on the product side. However many H's we have on the reactant side, we should have that many on the product side. That is the goal of having a balanced chemical equation. The same number of atoms on each side of the equation. So usually, for the most part, when you're balancing a chemical equation, you don't know yet how many of each atom there are. So it would be like if I gave you this photosynthesis equation, but took away these 6's and just gave you the CO2, the H2O, the glucose, and the oxygens. And said, okay, what are our coefficients supposed to be? How do we know how many carbon dioxides, how many waters do we have? That's what balancing chemical equations is all about. So in general, we're going to go through a whole bunch of examples today. So if you don't get it at first, don't worry. We'll do a bunch of examples, including a bunch of examples straight from the homework. So the basic steps are like this. You write the chemical equation, or in most cases, like on the homework, you have a basic chemical equation written out. You check and see how many atoms of each type do you have on either side. You see, okay, are we balanced? If not, then you have to go in, change around the coefficients, and try to balance the equation. After you change some of your coefficients, you'll go back and recheck and see, did you manage to make it so that you have the same number of atoms on the reactant side and on the product side. So just kind of talking through it and just explaining it in kind of very vague general terms doesn't really help. So let me walk you step by step through a kind of basic example to show you what I mean about all this. So here we have a pretty simple chemical reaction. Mercury oxide, so Hg is one of those weird ones where the symbol is Hg, but the atom is called mercury. Mercury oxide, HgO, turns into Hg and O2. So the HgO splits and becomes an Hg atom and an O2 atom. So we want to figure out, is this equation balanced? And if it's not, how do we balance it? So first things first, let's figure out how many of each atom are on either side of the equation. So we have our reactant side over here. We have our product side over here. And what I like to do, I like to write down the different atoms that are involved. So in this case, in this reaction, we have Hg and O are our two different atoms. So I write Hg and O over here. And then I make a little table. 1/2 for the reactant side, 1/2 for the product side. So I'm going to look at my Hg's first. Over here, there's only one Hg atom, so I write a run down here. Over on the product side, there's only this one Hg atom, so I'll write a 1 down here. Now let's go with the O's. On the reactant side, I have just the one oxygen, so I'll write a run down here. Over on the product side, there are two oxygens. So O2 means that there's two oxygen atoms that are bonded together. So we have two oxygens on the product side. So when we check for atom balance, 1 Hg and 1 Hg, those are the same, those are balanced, so that's a good start. 1 O and 2 O, this equation is unbalanced. There's one oxygen on the reactant side, but there's two oxygens on the product side. These numbers are not the same, so we have an unbalanced chemical equation. So we've identified that we are unbalanced. The next thing that we've got to try and figure out is what can we do in order to make it be a balanced chemical reaction. Oh, here we are. Forget that these arrows are in here sometimes. So 1 Hg, 1 Hg, 1 O. Over here we have 2 O's. That is unbalanced. So yeah, go for it, Ruben.
So we need to split that?
Not quite. Remember, this 2 down here, this is a subscript, and we are not allowed to change the subscript. We are not allowed to do anything with this 2. So if we can't change this subscript, we got to find some other way in order to make these O's balanced. So if we can't change this O into a 1, what are we going to have to try and do with this O? What are we going to try to turn this number into?
Could we add it? Or like
Coefficient, add a coefficient,
Oh,
something like that.
so if we have 2 atoms over here in the products, what if there's some way so we can make it where we have 2 O's over here in the reactants? Well, like I was saying earlier, we can mess around with the coefficient. Right now, HgO does not have any coefficients in front of it, so we only have 1 of each atom. So what we can do is, instead of leaving this a blank spot, we can put a 2 in here. So The nice thing about this is that now we have two O's, which is what we were looking for. However, HGO is a single compound. It's a HG and an O that are bonded together. So when we put this 2 here, we get 2 O's, but we also get 2 HGs. So this 2 applies to both atoms equally. 2 HGO compounds means that we have 2 Hg atoms and 2 O atoms now. So we can check for balance again. Over here, we have 2 O's, and over here we have 2 O's. Yay, we balanced our O's just like we were trying to do. Happy days. Uh-oh. HG not balanced anymore though. Now we've got 2 HGs over here, but we've only got 1 HG over here. So we still do not have a fully balanced equation. 2 and 1 are not the same amount of atoms. So we know we are still not balanced. So there's 2 HGs in the reactants, thanks to this guy that we added. But there's only the 1 single HG in the products. So is there anything that we can do over on our product side to make our HGs balance out a little better?
Add a 1, because you already got the 1, so just add 1 more to the coefficient.
So we do add 1 more, you're right. But remember, it's almost like there's an invisible 1 right here. We already have the 1 single HG. So if we wanted to add 1 more, what we could do is change this to a 2 instead. So now we don't have 1 HG anymore, we have 2 HGs. So we change this coefficient to a 2, and now we have changed the number of HGs in the products to 2. So now let's see if we are balanced. We have 2 HGs on the reactant side right here, and we have 2 HGs on the product side right here. That's balanced. We have 2 O's on the reactant side right here. And we still have the 2 O's that we started with on the product side right here. So the O's are balanced as well. So HGs are balanced, O's are balanced. So now we have a fully balanced chemical equation. So our final answer, our final result, if you will, our final equation is 2 HGO produces 2 Hg plus O2. That is our final balanced chemical equation. All right, so I know that I just threw a whole bunch of ideas at you right there. We are going to do a whole bunch more examples, but is there anything already that people are totally lost on or totally confused about so far?
So I do have a question.
Yeah.
So did you essentially just add the one that was next to the HG and then the one that was below it to make it that 2?
Essentially, yeah. So like with this guy, when we added the 2 here, that made this go from there being 1 HGO to 2 HGOs. So now there's 2 HGs and 2 O's over on this side.
Right.
And when we put a 2 in front right here, that makes this from being 1 HG to being 2 HGs.
Okay, I got it. Thank you.
So that's where these 2's came from, is by changing that coefficient. Remember, we can never do anything with these subscripts right here. These always have to stay the exact same as they're originally written. We can only mess around with these coefficients here. And yeah, the first important thing to remember about coefficients is that if you add one to a compound like this, it applies to both of them equally. You could not just take this 2 and like stick it right in the middle here and have it only go to the O. That's not how it works. The coefficient has to go in front of the compound, and it will always apply equally to both atoms in the compound. Or if there's 3 or 4 atoms in the compound, it'll go equally to all of them. There's one more important thing to know about coefficients, and that is when they interact with subscripts. So I already mentioned that these subscripts down here are set in stone. You can't do anything with them. Sometimes you'll be in a position where you have to put a coefficient in front of an atom or a compound with a subscript. When you do that, you multiply the coefficient times the subscript. So like in this case right here, if we have 3 O2 molecules, 3 times 2 means we have a total of 6 O atoms. Same thing with this water example right here. If we have 4 water molecules, the 4 applies to the H and it applies to the O equally. So because H has a subscript, we multiply. So 4 times 2 gives us 8 hydrogens. The 4 also goes with the oxygen, but oxygen does not have a subscript. It's just the 1 O. So in 4 H2O compounds, we have a total of 8 hydrogens and 4 oxygens. So whenever you have a coefficient and a subscript that interact with each other, you'll always multiply them. So 3 times 2 gives us 6 O's in this case. 4 times 2 gives us 8 H's. And 4 times, again, this is like if they just have like a 1 or something down here. 4 times the 1 O gives us 4 O's. So coefficient and subscript together means you're going to do some multiplying. All right. Let me go ahead and pull some examples from well, actually, let me go ahead and show you what the homework looks like first, and then I'll have you guys help me work through a bunch of examples from the homework. So here is what the homework looks like. There's kind of a example one done for you up here. But essentially, it's a series of chemical equations where you have some stuff on the reactant side and some stuff on the product side. And it gives you these little boxes down here to figure out how many of the atoms are on each side and then change it around as needed. And then it also leaves you these little spaces for the coefficients up here so that you can put them in and change them around as needed. Again, we're going to do most of these as examples in class today. And also remember that this homework is going to be essentially a completion grade. So as long as you go through and fill it out and do your best to try and figure out the answers and turn that in, you'll get full credit for it, no matter if your answers are right or wrong. So with that being said, let me go ahead and pull up a whiteboard. I always have to remember where it is. I think it's under here. Yes, it is. And I can view. right, then let me share that.
This also involves looking at the tables, right? No?
Not really, not necessarily. Oops. All right, so let me look at another good CaO2, CaO. All right, so our first example that we are going to work on looks something like this. Calcium plus O2 oxygen gives us the compound CaO. So we have two different atoms here that we are dealing with, right? We've got our calcium
Ca1
and our
O2.
oxygen. All right, so I think Namarique was just calling it out, but how many CAs do we have over here on the, so this is the reactant side, and over here is the product side. So how many CAs do we have over on the reactant side?
1.
Precisely. And how many O's are on the reactant side?
2.
Hey, very good. 1 Ca and 2 O's because of this guy right here.
Mm-hmm.
What about over on our product side? How many CAs do we have?
1 and 1.
1 Ca and 1 oxygen. Exactly. So just the 1 Ca, 1 O that are bonded together. So check for atom balance. Our CAs are starting off as balanced, so that's pretty handy. Our oxygens are not balanced, right? 2 is not equal to 1. So we are not balanced. We've got to do something in order to fix this unbalanced equation. So since our CAs are already balanced, I don't want to start messing with them. So let's focus on the O's first. We have 2 O's over on the reactant side and 1 over on the product side. We cannot do anything about these 2 over here because this is a subscript. We're not allowed to change the subscript. So what can we do?
Change another side too.
What was it? What can we do with this guy to make it be 2 O's?
Make O2 another side.
So we can't put a 2 down here because remember, that would be messing with the subscripts and we're not allowed to do that. So we can't change that guy into a 2. But we can do something with the coefficient out here in front of the atom. So what could we put there that would make this O be a 2?
2 CaO.
2.
Yeah.
Yeah.
Exactly. We could put a 2 right here. So this 2 is going to apply to our O because again, it goes to both these guys. So now we don't have 1 O anymore. We've got 2 O's. Yay, that's what we were trying to do. This is equal now. Happy days. But, this 2 also goes to our Ca, right? So now we don't have 1 Ca on this side anymore. We've got 2. So our O's are balanced and equal. Yay! Our CAs are no longer balanced and equal. Oh, bummer. So our O's are balanced now, so that's good. So I don't want to try to mess with the O's anymore. I have 2 CAs over on this side. So is there something I could do with the CAs over here in order to make them also equal to?
Add a 2 to the CA.
Yeah. So we could change the coefficient of the CA to be A2. Now, we've got 2 CAs on the reactant side, which is equal to the product side. So it looks like we have a balanced chemical reaction, but I'm going to go through one more time and make sure. We have 2 CAs on the reactant side, and we have 2 CAs on the product side, so that checks out. We have 2 O's on the reactant side, and we have 2 O's on the product side. That checks out. We have an equal number of CAs on either side. We have an equal number of O's on either side. So this is a fully balanced chemical equation. So our final equation is 2Ca plus O2 gives us 2CaO. 2 calcium plus oxygen produces 2 calcium oxide. All right, very nice work, everyone. We identified which atoms were out of balance. We adjusted the coefficients accordingly. We adjusted them again when we had to fix the CAs, and then we ended up with our final result. All right. Any questions before we move on to the next example? Anything that we did in here that you're still not really sure about or kind of confused about why we did it?
So I'm pretty confused on why it wouldn't end up being 3, because if you're adding the 2 and you already have 1 coefficient at the bottom of the CA.
Got it. So with the coefficients, when they are left blank like this, like you said, we had the 1 CA to start off with. Imagine that there's like an invisible number 1 right here. So if there's not any coefficient written, it's like there's a number 1 that we just didn't bother to write in. So it's telling us that if there's no coefficient, that means that there's 1 single Ca atom in our reactants. So if we change this coefficient, if we bump it up, instead of not being there or being similar to 1, if we bump it up to a 2, we've only increased the amount of CAs by 1. Because before, there was 1 CA, but when I write this 2 in, it tells me that there are 2 CAs. So there's not 1 anymore, there's 2. So the 2 doesn't mean that you're adding in 2 extra CAs that weren't there before. It's essentially just saying that before there was 1 CA, but now you've bumped it up to make it where there's 2 CAs.
Okay, that makes sense. Thank you.
All right, awesome. No problem. So that's the exact same thing that was going on over in the product side. Before, there was just 1 CaO compound that was together. But then when we wrote in that 2 for the coefficient, we said we're adding 1 more to give us 2 CaO compounds. All right, that's something that people get confused about a lot when they're first figuring out the whole coefficient stuff. So thank you for bringing that up. All right, so that one was a pretty simple, basic example. It was really similar to the one that we did for our example 1 from the notes. So let's try a slightly more complicated one. So now I'll go ahead and leave the little blanks for the coefficients to remind us that they're there. Now we have nitrogen, N2, plus hydrogen, H2, produces NH3, the compound NH3, which is, I believe it's either nitrite or nitrate. I can't remember which one is which. All right, N2 plus H2 produces NH3. So the first thing that we have to do is identify the atoms that are involved. So what are the two different atoms that we're dealing with here?
N3, H3.
Close, kind of. So the two different ones are just N and H, right?
Oh.
Those are the different atoms that we have.
Yes. And
So
2.
some of them are N's and some of them are H's. So we have the reactant side on this side again. We have the product side on this side. So over on the reactants, how many N's do we have?
3.
2.
2.
Here
Two.
2 and this one. Yeah, okay.
So on the reactant side, we have N2, which means we have 2 nitrogens. What about hydrogen? How many hydrogens are on the reactant side?
2.
2.
2, precise. 2 hydrogens. All right, let's hop over to the product side. How many nitrogens are on the product side? How many N's in the products?
Would it be 3?
1.
It would not be 3. It would be 1. Yeah, I heard somebody say it.
1 H3.
1 N on the product side. So this N and this compound NH3, this means that there's 1 N and 3 H's. So the subscript only goes with the letter that it's right next to. So just like H2O means that we have 2 hydrogens and 1 oxygen, NH3 means that we have 1 nitrogen and 3 hydrogens. So that is our starting count of atoms. 2 nitrogens and 2 hydrogens, 2 N's and H's on the reactant side, 1 N and 3 H's on the product side. Oh boy, this one is right off the bat, nothing is balanced, right? 2 is not the same as 1. And it is also 2 is not the same as 3. So we have a very unbalanced equation here to start off with. So the other thing that trips students up a lot when they have the different atoms that are unbalanced is that they don't know where to start. And my general rule of advice is always start with the smaller amounts. Whichever atoms have the fewer numbers, the fewer amounts, try to start off with balancing those ones and then see kind of where that takes you. So in this case, hydrogen has 2 and 3, nitrogen has 2 and 1. So I'm going to try to balance the nitrogens first. This is the smaller numbers up here. So I'm going to see if I can make the nitrogens balance first. So we can't do anything about this 2 over here on the reactant side, right? It's always going to be a 2. It's a subscript. We cannot do anything about it. So is there anything that we could do on the product side to give us 2 N's instead of 1 N?
You can put a 2 next to it.
Yeah,
Exactly. We could put a 2 in the coefficient spot right here, right next to him. So that would definitely give us 2 N's, right? This 2 goes to the N and it goes to the H. So we no longer have 1 N, now we have 2 N's. So yay, that's a good sign. We just balanced our nitrogens. And then let's see what happened with our hydrogens over here. They're already unbalanced. And now we have 2 N's, but how many H's are we going to end up with?
we're gonna multiply, so it's 6, right?
Hey, exactly. Mr. Bueno remembers. Right. Remember, whenever a coefficient and a subscript interact with each other, you multiply. So in this case, we do 2 times 3, and that is going to give us 6 hydrogens. So we started off with 1 N and 3 H's, and then we put a 2 here, which doubles everything. So now we have 2 N's and 6 H's. 2 times 3 is 6. So our N's are balanced now. That's nice to see. Our H's are pretty unbalanced. So because our N's are balanced, I don't want to do anything more over here if I don't have to, right? If I mess with this at all, it's going to change my number of N's, and I don't want to change them if I don't have to. They're already nice and balanced. So we have 6 hydrogens on the product side. Is there something we could do on the reactant side to give us 6 hydrogens? Is there anything we can do with these hydrogens to make it so that we have 6 hydrogens instead of 2 hydrogens?
Would you put a 3?
Yeah, you would put a 3. So if we make this coefficient into a 3, now we have to multiply again. And what is 3 times 2?
6.
It is 6. Oh, look at that. Things are looking up for us here in nitrogen hydrogen world. 6 and 6 are in fact the same number. So it looks like we have now balanced our chemical equation, but let me go through and double check. We have 2 hydrogens, or 2 nitrogens, 2 N's on the reactant side, and 2 N's on the product side. So this checks out. We have 3 times 2 is 6 H's on the reactant side, and 2 times 3 is 6 H's on the product side. So this checks out as well. So this is our final answer, our final equation. N2 plus 3H2 produces 2 NH3. We have now fully balanced the chemical equation. There's 2 nitrogens on the reactant side and 2 on the product side. There's 6 hydrogens on the reactant side and 6 hydrogens on the product side. Nitrogens are balanced, hydrogens are balanced. We have a fully balanced chemical equation. N2 plus 3H2 produces 2NH3. All right, thank you for helping me with that one. Is there any more questions, concerns, issues, anything about this example that we did that you're still kind of confused on or still not really sure where some of these numbers came from.
So I just want to make sure that like the bottom row has to be the same and the top row has to be the same. Okay.
So yes, the nitrogens, we have to have the same number of nitrogens on the reactant and product side. And we have to have the same number of hydrogens on the reactant and product side. We do not have to have the same number of nitrogens as we do of hydrogens, right? So in the last couple examples that we looked at, I think everything ended up being 2, right? 2 CAs and 2 Os, or 2 HGs and 2 Os, which is just kind of a coincidence. The only thing that matters is that your reactant side of one atom and your product side of one atom are the same. This being the same as this doesn't matter, doesn't count. We don't care about that. We only care that the nitrogens are the same on both sides and the hydrogens are the same on both sides. So it doesn't matter that we had 2 nitrogens on both sides and 6 hydrogens on both sides. The only thing that matters is matching each type of atom. So however many you have of N on one side, you have to have that many on the other side. However many of H you have on one side, you have to have that many on the other side. All right, great question. Ooh, the next one is a good one. So our final example from the homework, we'll take it up another step and make it a little more complex. Because now, instead of dealing with 2 different atoms, we're going to deal with 3 different atoms. So we have Cu2O, which is copper oxide, plus C, carbon, produces Cu, copper, plus, oh man, I really ran out of room, CO2. Writing letters with a mouse on a computer is a skill that takes a while to master. Okay, so our equation to start off with is copper oxide plus carbon produces copper plus carbon dioxide. Cu2O plus C produces Cu plus CO2. So first things first, we got to identify our atoms. So we have Cu, copper. We have O, oxygen. And we have C, carbon. So, how many Cus do we have on the reactant side?
2.
2.
Precisely. How many oxygens on the reactant side?
1.
1, precisely. And how many carbons?
1 as well.
Exactly, also 1. What about on our product side? How many coppers do we have?
1.
1.
1 copper. How many oxygens do we have?
2.
2.
2, exactly. 2 oxygens. And how many carbons?
1.
1.
Exactly. So 2 CUs, 1 O, 1 C on the reactants, 1 CO, 1 C, and 2 O's on the products. All right. So it looks like we have 2 different atoms that are unbalanced. Our carbons already look like they're nice and balanced, so that's neat. But copper and oxygen are unbalanced. So they're both unbalanced in the same way. We have 2 of one on one side and 1 of one on the other side. So in this case, I'm just going to say, let's start off with trying to balance the copper and see where we go from there. So we can't do anything about the 2 on this side because that's a subscript that is written in stone, that is permanent. So what could we do on the product side in order to give us 2 CUs?
Put 2 front CU.
Exactly. We could put a 2 in front here in the coefficient spot. So 2 CU gives us 2 CUs, not 1 CU. And so now we have 2 and 2. So our CUs are balanced. Neat, cool, awesome, good work. Moving on to oxygens, we have 2 oxygens on the product side. That again, we can't make that any smaller because that is a subscript that is permanent. So instead, what could we do over here on the reactant side to make it so that we have 2 oxygens?
Would you add 2?
Where am I going to put that 2?
Front CU.
The coefficient.
So yeah, the coefficient in front of our CuO over here, right? This O is the guy we're interested in. So we'll put a 2 right here. Bingo, bango, bongo. So now we have 2 O's right here. So that O becomes a 2. And that guy is all balanced. All right, awesome. 2 O's, 1 C, 1 C, 2 Cus, 2 Cus. Do we have a fully balanced equation now?
Yes.
No.
Oh, did
Yeah.
I make a mistake somewhere?
Yeah, carbon is still 1, no?
Carbon's still 1 on both sides.
And then there's 2 on each side for the second.
Oh, yeah. Sorry, I didn't see that other one.
Yeah, there's carbon over here. I just saw it. I put the 2 with the O, but I forgot to put it with the Cu right here. Right, because this 2 goes to both of them. It goes to the O and it goes to the Cu. So
4?
we actually, we end up making 4 Cus on the reactant side. So we balanced our O, which is good. But in the process of that, we unbalanced the Cu, which is okay. Sometimes that happens. Sometimes the initial way you have it balanced might not actually be the final answer. So we balanced our O's, so that's good. But now we have 4 Cus on the reactant side.
Yeah, you can put 2 C.
On the product side. So what, instead of having this 2 over here, is there anything we could change this into so that we could have 4 on the product side?
Change middle side. C.
Well, the C, we want to keep the C the same because we still have the C is all balanced out. But so we have 4 Cus on the reactants. So what could we do on the product side to also give us 4 Cus?
Would you add 2 more?
And so what
2 CO.
are we going to change this number into if we add 2 more? What is it going to be instead of a 2?
A 4.
Precisely. So whenever you're dealing with coefficients, if you ever have one there, but you want to add to it, essentially all you're going to do is erase and put in your new number. So we started off with 2. Well, we started off with 1. Then we added 2. But that ended up being unbalanced. And we saw that we actually need 4 CUs. So we can change that 2 to a 4 instead. Now, this changes to a 4. So it looks like we are all balanced, but let's double check one more time. So we have 2 Cu2s, which gives us 4 total Cus on the reactant side. And we have 4 Cus on the product side. So that's a good sign. That checks out, 4 and 4. We have 2 Os on the reactant side. And we have 2 Os on the product side. So 2 and 2, that checks out. We have 1 C on the reactant side and 1 C on the product side. That guy never changed. So now we have 1 and 1. So now we have a fully balanced chemical equation. 2 Cu2O plus C produces 4 Cu plus CO2. 2 copper oxide plus carbon produces 4 copper plus carbon dioxide. All right, so I really like this example because it's a great way of showing that it's okay to unbalance something that was already balanced, right? We started off, the first thing we did was balance our Cus, but then when we went to balance our oxygens, we ended up changing the Cus, and that's okay. Sometimes you need to do that before you get to the final answer, the actual final balanced equation. All right, so 4 and 4 coppers, 2 and 2 oxygens, and 1 and 1 carbon mean that our equation is fully balanced. We have the same number of each atom on the reactant side as we do on the product side. All right, anybody have any final questions, comments, concerns, anything about this balancing process that you're still totally lost or totally confused on? All right. So let me pop it back over to the homework. There we go. So like I was saying at the beginning of class, most of these examples we have already done together in class. So you may recognize the CaO was that first example we did on the whiteboard. The NH3 one was the second. This one was the one we just did, Cu2O. So I'll go ahead. There's one more that's on here that I'll leave for you guys to try and figure out by yourself. But remember, this homework is a completion grade. So as long as you try to figure it out and put in your best guess, then it doesn't matter if you get the right or wrong answer. You'll still get full credit for the homework. So I think it's a 5-point assignment. So as long as you turn the homework in with all of the questions answered, even if they're not the right answers, you'll still get the full 5 points for turning that homework in. It's my little gift to you guys for working on these with me and for trying this out. I know it's super complicated and it's hard to get after just one class period, Unfortunately, we don't have extra time to really work on this and do a ton of examples over like the next week or so. So because of that, I decided to just make this assignment a completion grade. So as long as you get it turned in to me with all of the questions answered, all of the coefficients that need to be filled in, then you'll get full credit just for getting it turned in to me and attempting to answer the questions. So that is the assignment for today. And then the one for tomorrow, the attendance assignment, is just a simple question about those coefficients and what they do in a chemical reaction. So make sure to be on the lookout for that posting on Friday. As always, I'll post a reminder to do that to make sure you earn your attendance credit on Friday. All right. Does anybody have any final questions, comments, concerns about any of the balancing stuff or any of the homework stuff that I talked about today?
I got most of it.
Good,
I
good.
got lost on the 4. When you changed the 4, that's where I got lost.
Yeah, and that one's tricky because it's like you started off with it balanced, but then you had to go back and change it a little bit. But getting most of it, getting sort of the basic idea down, that was really kind of the main goal for today.